So we want to find a unit vector in the direction of that given vector. And the way that we're going to approach this, let's call the, oh, please don't do that. Those dots.
Cursive is smartboard.
This pen will have to work better. All right. So we'll call the vector v, and wow, looks really thick. What is the first thing that we want to do if we want to find a unit vector in that direction?
Find the magnitude.
So we're going to find the magnitude of this vector. This will be done by using the square root of the sum of the squares, and we use the absolute value notation to represent it. And that gives us 9 plus 9 plus 1. So the length of this vector is the square root of 19. Any issues with that? Does that look good? So then what do we do? So we've got this vector, square root of 19 units long. We want a unit vector that's pointing in the same direction. So we do, yeah?
You divide the 3, the negative 3, and the negative 1 all by square root of 19.
So we take that square root of 19 and we divide it into each component of the vector, and then what we've done is scaled it back to be a unit vector. Exactly. So we'll write that as v divided by the length of v, and that will be this vector right here, and we're golden. This is a unit vector, and to check that it's a unit vector, you can find this vector's length, at least do it mentally, square, 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 add. So you get 9 over 19, 9 over 19, 1 over 19, 9 plus 9 plus 1 is 19 over 19. So it is a unit vector. So that is a unit vector that points in the same direction. If we wanted a vector that had length 5 and pointed in that direction that's given, what would we do next? Multiply by 5. Mm-hmm. Exactly. What about if we wanted a vector of length 3 that was in the opposite direction? Multiply by negative 3. Mm-hmm. Perfect. All right. Find a vector of length 24 in the opposite direction. We're going to start out again. Let's label this vector as v. We will find its length by doing the square root of the sum of the squares. Get 9 square rooted, which is 3. And the unit vector then, v divided by the length of v, this is the unit vector. We just divide each component by 3. So this is a unit vector that points in the same direction. Unit vector that points in the same direction. And we're trying to find a vector of length 23 in the opposite direction. So what do we multiply by?
Negative 23.
Yeah. So negative 23 times v over the length of v. And let's distribute that all in one step. So we multiply each component by negative 23. And that will do it. Any questions on that? 23, so another 46. That one's positive. So we get that. Simple enough? Straightforward? All right, so that is the end of 14.2. So then let's go to the homework, and I'll just do that on the same slides here. We'll just continue on. And let's pull up a couple of homework problems. And there was a question on number 2. All right, this is the one, I think. Somebody had a question on that one? Let's get it into our notes. Okay. So this is one of those navigation problems. We talked a little bit about this yesterday, how you can label things in lots of different ways. The idea is that you have a heading, you've got wind or current or something, and those two get added together to get your course. So that's kind of the way we're going to think of this. This one, let's see, so we said this one is a little bit slightly different just because we have current and we have wind. So let's take a look. So sailboat floats in a current that flows due north at 9 meters per second. So we're going to go due north 9 meters per second. Let's draw a vector to represent that. So 9 meters per second. Due to wind, the boat's actual speed, so that's kind of what we would call the course. Its actual speed is 9√3 in a direction 60 degrees north of east. So east and then 60 degrees north of east. So this is the course. Probably something like that. And we'll call that 5 square root of 3 meters per second.
9√3.
Oh, 9, thank you. And then it's asking us for, okay, so then it says assume that the vector W gives the speed and direction of the wind. So we're thinking about this one as the wind, that's W. And this one is, they're letting C represent the current. So I'm writing the C and the W without a vector symbol to represent the length of those vectors. So just keep that in mind, that this is pretty standard notation. If I want to indicate the length of W, I'll just write it like that, and the length of C, we'll write it like that. And we're going to call, so then it says, assume that W gives blah, 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 and that V sub G gives the speed and direction of the sailboat relative to the shore, which is, did I connect that vector in the right place?
No.
Where should that vector be? Where should it emanate from?
Tip.
Should emanate from the tip of the first vector, right? Because the wind is blowing, if you visualize it, the wind, if you're in your boat going this way and then the wind is blowing on you that way, the diagonal that's going to give your true course is going to be the diagonal that forms this triangle. So it should be attached to the tip of this vector. So let's move this stuff down, put that there, and let's see, where can I fit that so it's not totally in the way? Put it over there.
That's the same vector, right?
One wrong.
Say that once again, Haley.
It should be VG, V sub G, not W.
They said that, the true speed, yeah, we should call that V sub G, thank you. Yeah, we should call that V sub, So V sub G is the actual, that's the one that they're giving to us. So they're saying that the actual speed is 9√3 meters per second in a direction 60. So that is actually where we end up. Because that is I labeled it W and then I interpreted it as W, but it's actually V sub G. They tell us that's what we end up doing. We end up moving 9√3. So that is the course after the wind has blown us off of our drift. So that, I did have it drawn in the right place, but I labeled it wrong, so then I interpreted it incorrectly. So this is 9√3, sorry about that. So this is V sub G. And the wind that we're trying to find is blowing, like I said, it's blowing, if we're drifting this way, the wind is blowing us so that we end up over there. Yeah, sorry about that. So that will be our wind right there. Okay, and they tell us the angle is this 60 degrees north of east. So if we put in a little dotted line right here, 60 degrees north of east is telling us that that is 60 degrees right there, which tells us that this angle inside those two blue vectors is 30. That has to be a right angle since the current is going due north. All right, so now we're rolling. Okay, so let's form the equation. If we look at the picture here, we can see that we're going to add the current plus the wind to get V sub G. So current as a vector plus wind as a vector is going to give us the velocity with respect to the ground, with respect to the shore, however you want to think of it. the velocity of the actual course that you move along, however you think of it. And we want to solve for wind, so wind is going to be Vg minus C. So that will be D, or whatever it is, A, Vg minus C. Okay, so let's find the wind vector. To find the wind vector, we have to take and form V and C as vectors and then take the difference. Not too terribly complicated. Let's start with the C vector. So the C vector is due north, and we're only considering these velocities. And so what is that going to be? Is 0, 9? Everyone okay with that? 9 and 9 right through. Just want to double check that it was 9. Simple enough. Okay, now the more complicated one, we have to do this process of scaling a unit vector. We know the magnitude of the vector is 9√3. We know the direction is at 60 degrees. So what we want to do is form a unit vector that points at 60 degrees and then scale it by 9√3. So we're going to call V sub g as a vector 9√3 multiplied by the unit vector that points in the angle of 60 degrees. And that unit vector is cosine 60 sine 60. Right? We always do cosine first, sine second. So cosine 60 sine 60, cosine 60 is 1/2. And sine of 60 is √3/2. So that is the scaled unit vector that will represent our velocity with respect to the ground. So right there, that's the unit vector. And we scale it by the length of the vector, which is 9√3. Any question on that? So whatever the angle is, we put cosine comma sine of that angle. If we're at 45 degrees, cosine 45, sine 45. If we're at 80 degrees, similar. Now we subtract the two. So the wind vector is going to be this one. Let's distribute that in, so we get 9 square root of 3 over 2, comma. When we distribute the 9√3 there, we get 9 times 3, which is 27. So we get 27 halves. We're going to subtract off C, so I'm going to write it right below it so I can subtract really easily. And I'm going to write that just to make my life even simpler. Let's write it as 18 halves. So the wind is then described by this vector, 9√3 over 2. We have 27 halves minus 18 halves, so we get 9 halves. There's our wind vector.
This above should be Vg.
Say that again?
Above the C vector, it should be Vg. Yeah, you have two W's. Yeah.
Oh, did I write the... Oh, right here?
Yeah.
What the heck? Why do I keep writing that as the wrong... Good grief. Thank you. I'm seeing it correctly. I'm subtracting correctly. Ooh, thank you. All right, so subtracting, we get that vector. That's our wind vector, component form of our wind vector. If we want the speed of the wind, all we have to do is find the magnitude. So the magnitude of the wind vector, that is the speed of the wind. It's the length of that vector. So we're going to square, add, take the square root. When we square this, we're going to get 81 times 3 over 2. 81 times 3 over 2. Square that, we're going to get 81 over 4 actually down here. And then we have to add those together, and we need to then take the square root. So simple way here, I see that there's an 81 over 4 that's, or actually if I just factor out the 81, then we get 3/4 plus 1/4, which is 1. So this is all going to be 9. So that'll be the speed of the wind. 9, and our units, were we in? Meters per second. Thank you. Meters per second. All right, any question on any step there? So thinking about the picture again, we're told the current is 9 in this direction. We're told that the result, or the course, is 9√3 in that direction at 60 degrees. The way we get over to that course is by the effect that the wind has on us drifting. So that is how that picture makes sense to us. Current is going north, wind is going northeast-ish in that puts us on a course where we end up at 60 degrees north of east. All right. Now, did it also ask for the angle?
Yes.
So we have our vector components. Very easy to find the angle if you're given the vector components by using the tangent function. Tangent is y divided by x. So let's take a look at this. Let's put a little line there. So we're going to want to know what this angle is in here. I'll call that alpha. And what we can say is that the tangent of alpha is going to be 9/2 divided by 9√3/2. So that's y over x. Tangent is always equivalent to slope, rise over run. And the 9/2 cancel. We get 1 over √3, which if we write it in rationalized form, tangent alpha equals √3/3. You should be familiar with the unit circle. You should be familiar with the fact that at 60 degrees, that slope is √3, and at 30 degrees, that slope is 1/3 of √3. So if we have tangent of theta equal to √3/3, we know that our angle's at 30 degrees. And if we're at 60 degrees, our tangent is √3. So we're sitting at an angle alpha of 30 degrees. And now, Michael, you had asked something about this, so now we have to talk about how to describe that. If that's 30 degrees, in all the old books, we would have said north 60 degrees east. In the old books, you always did north or south first, and then you did east or west. This book seems to do the opposite, does east or west first, and then goes north or south. So we would describe this as east 30 degrees north. Either one is fine.
Yeah, it might be trying to align itself with conventional Cartesian coordinates
Since rotation is from the positive x, it's very possible that that's what they're doing. So east 30 degrees north, or you could go north 60 degrees east. So those are the same. Either one. Haley?
You say that 30 degrees north of east?
Yes, this is 30 degrees north of east.
Okay.
This is 60 degrees east of north. Yeah. Yeah. That's how you would say it. Very funny. All right, let's take a look at number 7. Number 7. Let's see. All right, this is a good one. This is, I'm not going to include that picture because that picture takes up way too much space and it's actually a little bit misleading.
They do it in a really weird way. It's much easier. You think so?
Okay, with this ramp problem, the big key is to draw your triangles very carefully. And if you draw them carefully and you don't get too much stuff in the way, it will work out well. So first, let's imagine a ramp. And they tell us that the ramp has an inclination angle of, see, the object is 70, inclination angle is 30 degrees. So we have a 30-degree ramp right there. And I find it simplest, instead of drawing a big box on there and you have too many lines, I think it's really helpful to just imagine it as a point mass. So you put your point mass right there, and then the weight of that box is straight down. The weight is the force towards the center of the Earth. So that is a gravity vector right there. And then what we want to do is decompose that vector into 2 component vectors. We want to figure out what the component of this weight is with respect to the ramp, which they refer to as parallel to the ramp, and then we want to figure out the component that's perpendicular to the ramp. So what we do is draw 2 vectors that will add up to this weight vector. So we're going to draw one perpendicular to the ramp right there, and one down the ramp right there. And those 2 vectors add together to give you the weight vector. So we're just kind of going backwards. If I gave you those 2 blue vectors positioned in this way, you would say, oh, the triangle rule says the sum is this vector that goes straight down. So we're going backwards, which they call decomposition. We're turning this vector into a sum of two vectors relative to, in this case, the ramp. We'll do this a lot later today also, where we're going to decompose a vector with respect to coordinate axes. So we form a right triangle here, and what you're going to notice is, if you're really careful, and we'll be careful, is that this angle right in here is also 30 degrees. So let's see, how would I know that? Well, let me outline another right triangle in here, and then I'll take it off, but I'll put it in there just for a moment. So there's a right triangle. So if that angle is 30 degrees, and this angle right here is a right angle, that forces this angle up here to be 60 degrees. Everybody okay with that? So that yellow triangle, 30, 60, 90. So we know that that angle up there is 60 degrees. So right in here, we have a 60-degree angle up there, 60 degrees. Well, then we have a second right triangle, correct? Right here, there's another right triangle. That's 90 degrees. So this must also be 60 and 30. If that's already 60, we know that this one's then 30. And in the long run, after you've done about 3 of these, you realize every single time when you draw your force triangle that whatever that angle is, it's going to match that one right there. Now we just have to label those blue vectors. One of them is the force parallel to the ramp, and one is the force perpendicular to the ramp. Call it whatever you want. I'll call this one force parallel with a little parallel symbol, and I'll call this vector force perpendicular with a little perpendicular symbol. You can write P-A-R and P-E-R-P if you want. It doesn't matter. And if we pull out the triangle here, well, we don't even have to pull it out. Let's just start doing it. So you can either focus on the 60 or you can focus on the 30. Doesn't matter. If we use the 30 and we want to figure out what F parallel is, we're going to use the sine function. The sine of 30 will be opposite over hypotenuse, and the hypotenuse is 70. Oh, we have a little bit more going on here. They gave us the mass, not the weight. So how do we find the mass from the, how do we find the weight from the mass? Multiply it by gravity. So if we have mass and we want weight, weight is force. Mass is not force. Mass is a scalar. So we need to take our mass, multiply it by our gravity to actually get the force here. And what happens when you multiply 70 by 9.8? What do you get?
6.8 newtons.
6.8?
Oh, so 686, my bad.
686 newtons. Okay, thank you. Okay, so that's our force there. So now we just use right triangle trig. So we're focusing on the 30. So if we do sine of 30, we get opposite, which is the force parallel. And now notice that I took away the vector symbol. Because now I'm thinking of a right triangle with just legs that have numerical values. So F parallel without the vector symbol is the length of the actual vector. Okay, it's the magnitude of the vector. And so this tells us that the force is going to be 686 times the sine of 30, which is a half. So we get 343 newtons. That will be the force parallel. So in other words, if we're applying a force, and we're imagining this right now as a frictionless surface, so that's the force at which this block is going to want to slide down the ramp. So if we want to stop the block and keep it stationary, we need to apply a counter force up the ramp of 343 newtons. All right. Now, of course, that's not reality. There's going to be some sort of coefficient of friction on that ramp. Usually they call it mu. And then there's a relationship between F perp, F parallel, and mu, and the angle. And you can figure out what the angle is. There's a problem, I think, later in homework that has to do with that. But you can see how those are all related then. So F perp, instead of 686 times sine of 30, it's going to be 686 times cosine of 30. And cosine of 30 is root 3 over 2. So this is going to be 343 root 3 newtons. Now, of course, you could have also used the 60. But here, if you use the 60 to get the parallel, you would use cosine of 60. And if you use the 60 to get the perpendicular, you would use sine of 60 to get the perpendicular one. So it doesn't matter. Those are co-functions. Sine of 30, cosine of 60, same. Sine of 60, cosine of 30, same. So either way. But I think it's a lot easier to write this picture in two-dimensional space, trying to draw the block like they did it in that picture. Just there's too many arrows and it starts to look a little difficult to discern what's what. So keep it simple. Make your weight a point mass. Any questions on there? All right. 14. Let's see. Do we have 30? Might not be able to get through both of these.
I think the problem I'm thinking of is like the hanging
Let's take a
table where
look.
there's three tables.
14.
Maybe, or there's another block problem that's like this.
14.
These
Ah, that's a good one.
That's what it is.
Oh, these are about the same. So let's do one of these, and then you can
These ones were.
piece it together and get the other one. Let's do the 14 one. All right, so this is dealing, this sort of ups the ante and we're dealing with three-dimensional space. So we're dealing with three-dimensional space here. We have to be a little bit cautious. It gets a little bit confusing, perhaps. So first it talks about this plane flying due east in calm air, 250 miles per hour, and then it comes across this northwest wind and this updraft. Let's forget about the updraft for a minute, and let's focus just on two-dimensional space. So when we graph navigation problems in two-dimensional space, we're going to typically go north, east, this direction, that way. That's how we'll label it. Bless you.
Thank you.
So let's focus on the pieces that don't involve the updraft first, just to make sure we have a good picture of what's going on. So flying horizontally due east at 250 miles per hour. So let's draw a vector that represents that velocity. So due east, and that's going to be, we'll write a vector length of 250 on there. And then hit by a horizontal crosswind blowing northwest at 30 miles per hour. So it's blowing to the northwest. When they say northwest, they mean right in the middle of north and west. So bisecting quadrant 2, the way I've drawn it here. So we're going to draw this vector up here that's bisecting this quadrant right there, and that is a 20-mile-an-hour wind. Maybe I'll stretch this out just a little bit longer. Maybe I'll shrink that one just a little. So 20 miles per hour for that one.
That's 30.
30 miles an hour. Oh, the 20 is the up. Okay, good. Thanks. So 30 miles an hour for that wind right there. Okay, so that gives us a kind of a picture of which direction, what's happening. So if we wanted to, we could draw a parallelogram and kind of get the sense of how that wind is affecting this plane. But there's this extra updraft that's also affecting it. So now we need to try to draw this in three-dimensional space. And the book, what direction does it put north? Does it put north to the right? I think it does. I think it does it in a way that I found a little unintuitive. So let's draw a three-dimensional coordinate system. And let's,
It does do that.
right, it puts north to the right, correct?
Yeah.
All right, so we're going to do it this way. We're going to call that north. We're going to call, what would this one coming out of the board be then? East, right? So, and then, so then we're going to go south will be to the left, and that will be, let's use little dashes there. So that's going to be south, and then west is back that way. Okay, so now we're going to try to translate everything over to 3 dimensions. So the 250 east part, let's draw that. That's simple enough. That's coming straight. That's coming straight out of the board. Focus on that. So there's our 250 east, and then we have to draw our wind, our crosswind northwest. So northwest is back in here. So let's make it a different color. Northwest is back in this quadrant. And then the updraft, which is 20 miles an hour, that's straight up. So that's going to be our third vector that has to get added together. and that one is straight up. And let's label these numbers. So that one's 20, that one's 250, and that one's 30. Okay. Very difficult to look at that three-dimensional picture and try to draw a parallel pipette and the diagonal across that parallel pipette. That would be very difficult to do. So we won't do that. But what we will do is create component forms for each of those vectors, add them together, and that will tell us where the resultant vector is. So let's go ahead and create component vectors for everything. So we're going to have if we use this, we're going to use this direction as x, that direction as y. So we're going to do east and then north and then up. All right, so that vector right there we're going to call 250 and then 0, 0. And then how about that vector right there, the one that's blowing, the wind that's blowing northwest? How can we create the component form for that wind vector?
Negative 30 cosine 45, 30 cosine 45, and 0.
I think what you said is
30
right.
sine 45.
We know the vector is 30 long, so we're going to put that out in front, and then we have to scale a unit vector, and you said 45 degrees. And the reason you said that is because this reference angle is 45, but we have to remember that instead of going forward, we're going backwards, so we put a minus sign in there. So we're going to go minus root 2 over 2, comma, root 2 over 2. And this is a crosswind, so there's no z. There's no. Jeez. All right. So there's no z component. That z component is just 0. So does everybody agree that that's the wind, the crosswind?
Why is it not negative on both root 2 over 2?
So and that's why I drew this picture. So when you look at this picture, you're going left, which is negative, and then up, which is positive. So when we come over here, back is negative, but then this is in the positive n direction, the positive y direction if we were using our standard coordinate system. And northwest is bisecting, so you get the 45-degree reference angle.
Just making sure you're basically taking the sine and cosine of 120 degrees, right?
Of 135.
135, sorry.
Yes, 135. Absolutely. That's right. You can think of this right here, that standard angle is 135 degrees. So that number is cosine of 135. That number is sine of 135. Or you can use the geometric idea that the reference angle is 45, so you have root 2 over 2 and root 2 over 2, but then it's left, so it's negative. Either way. And then the updraft, piece of cake, that one is just 0, 0, and it's going up at 20, so we get that. And we just add all those together. So we're going to have our first component is going to be 250. And we have to distribute this 30, so it's going to be minus 15 root 2, comma. The middle components will be 15 root 2 plus 0. Last component is just 20. So this is the resultant vector. This is the vector that's pointing to the direction that we're ending up after all this, the direction of flight, the course. So, do you agree that all of these are positive numbers? Yeah, they're all positive numbers. This number is definitely less than 250, this negative part. So we're in octant 1. And we can't, trying to draw that's a little complicated. You can imagine this parallel pipette with this vector coming out into octant 1. And then they give you some sketches and you have to try to pick the right one. So if you look at the octant 1 result, we know that it's going to be a vector that's pointing above the xy plane and it's coming out into octant 1 a little bit. And if we want to figure out angles, you could do some angle calculations, but I don't think they ask you to do that. It's a little complicated in 3 space, but it is possible. One more?
When we're turning in homework, if we ever do you want us to leave it in this similar form, like 15 root 2, or do you want us?
So it
like
depends on
exact
what you're
form,
asked
or-
for. So if it says leave it in exact form,
No.
you would leave it like that. And if it said to approximate,
Yeah, okay.
Then we would type it into our calculator and get the decimal expansion. So yeah, it's just going to depend. On the test, I'll be really clear. Find the exact value of or find the approximate value of.
Okay.
So really important to get what those two words mean. Exact means leave the square roots. Approximate means get the decimal expansion. So now, if we wanted to figure out what the length of this vector is, the length of that vector would correspond to the speed along that course, right? So we could find that very easily. Square, 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 add square root. Kind of a messy number to deal with, but if you're using a decimal expansion, you can just type that into your calculator, square it, add that squared, square root it all, and you get the speed. Okay, so let's go to hit save on this. So the next section that we're covering is 11.3, and I actually have some other examples in here from 11.1 and 11.2 that we may or may not do them all now that we've done such a wide selection of these. We did not do one like this, so I want to at least give you an overview of it if it's not clear to you already. So in this one, this is coming from 11.1. We've got an object with 3 forces being applied to that object, and we want to know what happens. So if you have 3 kids pulling on a rope that's attached to something that moves, we want to know what direction is it moving when all those forces interact with each other. So all we're going to do is find the component form for each vector, add them together, and that gives us the result. That tells us where we're going, tells us what happens when all 3 forces are applied to that object. So, again, this concept of scaling a unit vector cannot be understated. We do that a ton. So we look at force 1. Force 1, we could come up with the components in 2 ways. We could say that the standard angle here is 135 degrees, and we would do cosine 135, sine 135. Or we can look at the reference angle. The reference angle is 45, but we know we're going left and then up, so we apply a negative sign to the cosine of 45. Either one of those techniques works absolutely fine. They're indistinguishable in terms of the result. Force 2, we know that it has a magnitude of 60. So we're going to scale a unit vector to generate a component form for that vector. 60, okay, that angle's at 30 degrees. Cosine 30, sine 30 is the unit vector that points at 30 degrees. Force 3, that's way the heck over here. So, 2 choices. You could do cosine and sine of what angle? If you were doing the standard angle rotating from the positive x, 240. You could do cosine and sine of 240, or you could say, hey, reference angle is 60, so it's cosine 60, sine 60, but we're in quadrant 3, so it's negative and negative. Totally fine. So the only thing, if you're using that technique, the only thing you have to remember is how reference angles are used. In quadrant 1, theta and theta prime, the reference angle are the same. In quadrant 2, here's theta prime, and what's the relationship with theta? You have to subtract theta prime from 180. So this is in quadrant 2. In quadrant 3, reference angle's right there, and the relationship between theta and theta prime in quadrant 3 is that theta is equal to 180 plus the reference angle. Quadrant 4, reference angle's right there. In quadrant, Q. Quadrant 4, theta is equal to 360 minus theta prime. So if you're going to use the reference angle approach, you sort of have that geometric vision in your mind, how reference angles work and how they relate to the angle, the standard angle. Okay, now we just add these together. So let's rewrite each of them first. So F1 is going to be, we're gonna evaluate and distribute the 100. So that's root 2 over 2, distribute the 100, so we get 50 root 2. So we have minus 50 root 2 comma 50 root 2. And then F2, same idea. We're going to distribute the 60. Cosine of 30 is root 3 over 2. So we get 30 root 3. And then sine of 30 is a half. So we get that. F3. Cosine of 60 is 1/2. So we have negative 1/2. So what? Negative 75. And then sine of 60 is root 3 over 2. So 75 root 3. Negative. Okay, so those are the three vectors in component form after we've evaluated those trig functions. And then we add them all together. So the total force, we're going to have some messy looking numbers, but doesn't matter. We're not afraid. Just add them all up. Now we have a vector with two components with the resultant force. So that's our resultant force. So we can type those into our calculator, get an approximation, and see what it means. If we want the magnitude of that, same thing. Type it in the calculator, square it, type it in the calculator, square it, add them, and then take the square root. So that will be how you would approach that. Any questions on that? Yeah?
Yeah, if anyone's interested, I got the final vector as approximately negative 93.749.
Say that again, negative, just go to one decimal.
Negative 93.7 and negative 29.2.
Thank you. Did you get the length of it?
Length, not yet.
And so you know how to get the length. Square, square, add, take the square root. All right, let's take a look at another one.
Back to my earlier question.
Yes,
So on tests, how many decimal? If it says,
it'll tell you.
It'll tell you how many decimal
yeah.
points to go into.
Yeah.
Okay.
No mysteries.
Okay. Good.
Not that kind of mystery, at least.
Okay.
Yeah. Yeah, yeah. No, yeah, we will definitely, you will be told. Yeah. All right, so this is one like we just did. I'm not going to go through this one because we just did one. But you can look through this. This is exactly what we just did. So try that one if you want. All right, how about this one? Give a geometric description of the set of points that lie on the intersection of the sphere and the plane. So first off, what is that sphere? What's the radius? What's the center? Center is the origin, 0, 0, 0. Radius, square root of 5. Square root of 5 is more than 1. So we've got the sphere, and that plane definitely goes through the sphere. It's not above the sphere because 1 is less than root 5. So what you should be visualizing, you've got a sphere, you basically have a plane that's chopping off a cap. And so what they want is to describe what that intersection would be. So back in algebra, you did this all the time where you found intersections that were points. Now we have an intersection that is a curve. We do the same kind of thing, though. We plug one equation into the other to figure out what that intersection looks like. So we do that substitution type of thing. If you take the plane and plug it into the sphere, notice what happens. We get x squared plus y squared plus 1 equals 5. Subtract 1 from both sides, and that gives us x squared plus y squared equals 4. We know that that's a circle of radius 2 centered at the origin. Okay, so now it says describe. All right. So that's a circle of radius 2 centered at the origin. But remember that we intersected the sphere with a plane that was up there at height 1. So what we need to visualize then is taking that intersection, that circle of radius 2, and lifting it up so that it's floating at height of 1. Everybody follow that? So when that plane intersects, that tells us that all the points on that intersection have a height of 1. So we're going to have a circle of radius 2 centered on the z-axis at a height of 1. Does that make sense to everybody? So just plug one curve into the other. We eliminated the z, so that tells us that our intersection curve is parallel to the xy plane, and it's going to be parallel to the xy plane at a height of 1.
So does that just describe the curve, or does that describe the entire plane?
It describes just the curve of intersection. Right, so the sphere is here, and that plane intersects it, and there's only a band around that sphere that is the curve of intersection.
Okay, but wouldn't this set of all points lying on that intersection be a plane?
No.
No? But it's a sphere, so it's filled in, right?
The sphere is empty.
Oh, okay.
A ball is solid. So if we were dealing with a ball being intersected by the plane, then you're right, then we would get a disk. And so then we would do a less than or equal to thing, and we would have a disk that was at height 1 of radius 2. Yeah, good question. All right, let's take a look at one of these cable loading problems. There's one of these in the homework. And the book doesn't tell you, the homework doesn't tell you this, but it turns out to be what's happening. The 3 points there, you know, we did one the other day where if you had 2 cables at 45 degrees, so they're symmetric, we know that the force on each is the same. So that allowed you to use some symmetry so that you weren't solving a more complex system than you needed to solve. This is true here also, but they don't tell you. If you were to look at these 3 points, plop them in the plane, if you found the distance between each of those, you would find that you actually are dealing with an equilateral triangle. So they tell you that the cable lengths are the same, but that doesn't necessarily mean that you have perfect symmetry in terms of the angles. You could have 2 the same length right there, and then another one the same length over here, and sort of pull it so that it's not perfectly symmetric from every perspective. So if you do notice this, though, it's like, oh, okay, so that tells you that the magnitude of the force on each of those 3 cables is identical. And that allows you to solve it in a much more efficient way instead of solving a 3x4 matrix or a 3x4 system of equations. So when you're working on that one, use that extra information. It's very helpful. One other thing I want to say about this is that you've got to be a little careful with your signs, because the way that they construct this problem, notice that they put the unit vector pointing in the downward direction. And so normally when we are concocting a set of equations for a system, normally we say, okay, it's at equilibrium. So if we had something like this, if we had this cable situation like that, where we've got a weight on the 2 cables, we'll call that the left force and the right force, we'll call that the weight force. Normally what we would say is L plus R plus W is 0. That the system is at equilibrium. But when we're doing that, when we do that, that is sort of imagining this, that this vector is pulling up, this vector is pulling up, this vector is pulling down, causing balance. But the way they drew this and the way they ask you to move through the problem, these are actually in the same direction as the weight. Okay, so when you're adding up the z components here, you're actually going to be adding up to get to negative 500 instead of 500. So just be careful of the minus sign when you're doing it. It's going to be a little different than the one we did in class.
So just by their convention, does that mean that the force on that block or whatever is actually pointing in some upwards direction?
That's how you could imagine it if you wanted to use that same kind of logic, that the forces are counteracting each other. Yeah, it's a little funny that that's the way they constructed it, but you just have to be aware that it's going to be equal to minus 500 instead of equal to 500. Because normally if we have a 500-pound block, we're saying that's negative 500, and we need these other 2 things to add up to positive 500 to offset it. So here they're saying we're going to call that negative 500, and we're going to call this negative also, so we need negative 500 to equal negative 500. So it's a slightly different perspective, but it works. Yeah?
Are they doing that because they're anchor points?
I don't know exactly why they're doing it. I don't know exactly. Yeah, I'm not sure. You'll figure that out in physics too, right? And then you'll
Maybe.
come tell me.
Maybe.
Tell me when you take physics. Has anyone had physics that would know why they're pointing those vectors down? In physics, I thought you would point them in the opposite direction of the force to
I think it's just
balance.
wrong.
I think it has to do with
It's just
actually
different.
the origin is above.
Someone,
Yeah, maybe.
someone
yeah.
didn't take physics.
Yeah, maybe it seems too confusing to draw the vectors through the xy plane and directions not of the cables.
I took statics, and in statics they had those as reactions,
Mm-hmm.
and so it's like you said, they're anchor points,
Mhm.
and so the reaction, and it's like a two-force vector, because it has a here and it has a here at the same time, so it kind of works that way.
Yeah, that idea. You were just pointing up though for this one, which seems funny to me. But yeah,
They
okay.
offset either way.
They offset either way. Yes.
So you can do what you said, like have 500, or just remember to throw in a negative at the end.
Mm-hmm. Mm-hmm. Yeah. Either way will work.
On the topic of physics things that this book gets wrong, it keeps implying that the wind speed directly translates to a change in velocity. But that would be dependent on like surface area and
Correct.
inertia and all
Friction? In math, we ignore things like friction and coefficients of.
You guys have spherical cows. What do you
sorts.
want?
But what is that friction that when you're dealing with a plane, there's that the hydrofoil thing of the wing? I don't know. There's all those extra friction forces that you've got to. We're gonna ignore all those. We'll ignore them all. We'll ignore friction. There's no friction. We're just sliding along. All right, we are going to start 11:03. I feel like we might as well just take our 10-minute break now instead of doing 5 minutes of 11:03 and then coming back. So let's take our 10-minute break now, and then we will get to our context is force times distance. So if the movement is in the direction of the force, all we have to do is multiply the magnitude of the force times the distance. So if the direction of motion and the force are in the same direction, no problem, just multiply force times distance. You've already done that in other classes. If the force is not in the direction of motion, then what we have to do is decompose the force into two component vectors. One that's in the direction of motion and one that's perpendicular to the direction of motion, just like the ramp problem. So we want to decompose that force, and we want to figure out the component of force that's parallel to the ground, the component of force that's in the direction of motion. And then the work will be whatever the magnitude of that component is. And the magnitude of that component is the length of f times cosine. Let's figure out why. If we come down here, so if we have this as our force vector and we're trying to find the component of force in the direction of motion or the component of force perpendicular to the motion, all we have to do is use sine and cosine on the angle theta that defines the angle between the force and the direction of motion. Does everybody see how we would get those two, the x and the y components there? If those weren't there, if you just called that x and called that y, you would say cosine of theta is equal to x divided by the magnitude of f. And that would tell you that x is equal to the magnitude of f times cosine theta. Right? And you could also use sine. If you did the sine of theta would be y over f. So y would equal the length of f times sine of theta. So we'll do that a lot, where you find the components of a vector. So let's just write that one out. So sine of theta will be y over the length of f. And so that tells us that the vertical component is equal to that. All right, so, yeah.
Yeah, just out of curiosity, in these work problems in most of the practical applications, will we ever really be using the y component?
Yeah, not so much. Not for the work problems, but for other types of problems, we will use the perpendicular component of a vector a lot.
Alright, Yeah, 'cause-
We'll do a few applications today actually where we do use it.
Yeah, 'cause
But,
the main-
but not necessarily for force and work.
Yeah, the main reason I see it us using vertical is if you're trying to move something up a shaft and you're pulling it from an angle rather than from directly upward.
Yeah, we won't do that, but we'll do other stuff where we use it.
That would be a very practical way to pull something up.
No. All right, new definition, dot product. You may or may not have seen this before. This is a type of multiplication between vectors. So in the real number system, you can multiply vectors. There's only one. Excuse me. You can multiply scalars. You can multiply numbers, but there's only one way to multiply numbers. There's not two ways. What we are going to see with vectors is that you can multiply them with the dot product or with the cross product. So we use the two symbols that we use for numerical multiplication, and then we call them different things. So in numerical multiplication, 5 dot 4 and 5 cross 4, those mean the same thing. They're both the multiplication symbol. But when we're dealing with vectors, they're totally different. So if we do u dot v, that means that we want to find the dot product of two vectors. That is going to turn into a scalar. That is a scalar valued operation. So we're going to end up with a number there. Some people call this the scalar product in contrast to the dot product. It means more or less the same thing. So that's a scalar. And that value, u dot v, is very easy to find. You can do it in a couple of ways. This is sort of a, there's two main ways that you'll write it. This is one way, where we write it as the length of u times the length of v times the cosine of theta. And one thing that you should notice there, that if you form the dot product of two vectors, cosine of theta could be positive or negative depending on what theta is. So if theta is between 90 and 180, cosine's negative. So then you're going to have a negative scalar value for the dot product. So dot product can be positive or negative or 0. And this picture gives us the most important cases. If you look at this case right here, that's pretty typical. If you have an acute angle between two vectors, cosine of an acute angle is positive, so you're going to get a positive value for that dot product if you have an acute angle between two vectors that you're dotting together. If you have two vectors that are perpendicular, the dot product will be 0. So it's a really quick way to figure out if a pair of vectors is orthogonal or not, perpendicular or not.
So when it's called the scalar, why is it called the scalar?
Oh, we just use the word scalar to represent constants.
Okay.
So a scalar valued function is a function that gives you a scale, or gives you a number. So people will refer to scalar valued functions. Some people will call them real valued functions. It means the same thing.
Okay.
You know, so scalar is just another word for number.
Okay.
And the reason we call it a scalar in math and physics, if you think about a vector and you multiply it by a number, what does that number do to this vector? It scales it. So we think of, that's why we tend to call them scalars, because we think of them as multipliers that scale vectors.
So it's called that because that function basically removes the direction from it?
So this function right here, it just gives you a number. Like
Okay.
it's like the absolute value function. Like if we take the absolute value of a vector, don't we get a number? So we would say that that absolute value function or that magnitude function is scalar valued. The value of it will be a number in contrast to it being a vector. So we're going to come across a second type of multiplication called the cross product, and the output there will be another vector. We will see very soon that if we take two vectors and we cross them, we will end up with a third vector that is perpendicular to both. So the cross product will turn into a very useful type of multiplication, but that output is going to be a third vector. It's not going to be a scalar. So dot product, this multiplication gives us a number. Let's make sure it's clear in our head that this is a number. The length of u, that's a number. The length of v, that's a number. Cosine of the angle in between them, that's a number. Three numbers multiplied together is a number. So that's definitely a scalar. So that's a scalar valued function. And our three main cases here are these three main cases where acute angle, dot product is positive. So dot product is positive there, dot product is 0 there, dot product is negative there. So if the angle is acute, positive dot product. If the angle is obtuse, negative dot product. And if the angle is perpendicular, dot product is 0. Okay, so this really important formula, we will use that throughout the whole semester, for sure. Now here is a theorem that gives us another way to find the dot product. Because as you know, quite frequently when you're talking about vectors, you're given the components. And we're not normally given the angle between the two vectors, right? We're normally given like 2, 5 and 6, 3. There's no angle. We're not given the angle. So to use this definition, it's a little cumbersome because we don't know theta. So we would love a computational way to find that dot product that doesn't involve this extra work of finding the angle. And here it is. Here's the theorem. The theorem says you can find the dot product so easy. All you have to do is take the corresponding components, multiply them, and then add them together. That is the dot product between two vectors. Multiply corresponding components, add them up, you get a number. That's called the dot product. And that is it's not a super hard proof. There's a proof on page 783 of the book using law of cosines. Not that difficult. So one of our conclusions then is that we can write u dot v in either one of these ways. So we can write it as the length of u times the length of v times cosine of theta. Or we can write it like that. And so quite frequently, we're going to be setting these kind of things equal to each other. Yeah?
You may have just said this, but is this how you find the magnitude of the length or between the vectors? Or?
So the angle between the vectors.
Okay.
So if you're thinking about something really practical, if someone says, hey, what's the dot product for? The answer would be to find the angle between two vectors. Because if we have the components like we normally do, we can find the value of the dot product, put it right there. And if we know the components of u and v, we can find length u and length v easy. So then we can divide by that. Inverse cosine of that side gives us the angle. So the dot product's primary function is that it introduces trigonometry into the whole idea of a vector space. So if you've got vectors that you can add and subtract, natural question is how do you find the angle in between them? Dot product. Dot product finds the angle between vectors. Yeah?
Yeah, question. Yeah, so if you can easily find the dot product, wouldn't you be able to use that to find the angle between the two vectors fairly easily by just?
Yes, taking the inverse cosine of both. Yes, taking the inverse cosine of the dot product value. We'll do it in just a second. So let's look at a few properties for the dot product. Dot product, just like in multiplication, when you did real numbers, you introduced a new symbol. You wanted to figure out what the properties were. You had all those rules. Dot product, very similar. It's commutative, like regular scalar multiplication in the real numbers. It's commutative. And it's got an associative property and a distributive property. So the standard properties all come along with the dot product. When we get to the cross product, we'll see that that's not the case. There's going to be different properties. It's not going to be commutative, which is a weird one. Normally, we think commutivity comes along with almost every operation that we define. But when we do the cross product, it won't come along. Dot product is commutative, but the cross product we'll see is not commutative. OK. Yeah. So the next thing we need to talk about is something called the projection vector. Lots of applications with the projection vector. Lots of confusion with the projection vector because there is some notation that just is a little messy. The idea of a projection vector is very simple. We want to imagine finding components of a vector with respect to another vector. Kind of like we did the work problem, kind of like the ramp problem, where we had a force vector and we wanted to decompose it into two other vectors with respect to the ramp, or maybe with that wagon problem, if you're pulling a wagon, you want to decompose your force vector with respect to the ground. The projection vector is it generalizes that idea of projecting one vector onto another. So let's take a look at that. So and they call it an orthogonal projection because you're projecting down in a perpendicular way. So we're projecting u onto v here. And there's two cases. Either we have an acute angle or we have an obtuse angle. let's forget about the obtuse angle for now. It's going to turn out that all the formulas work regardless of whether it's acute or obtuse, but it's much easier to understand and to sort of follow the logic if we think about the acute case. So we're imagining that we're projecting vector u onto vector v. And we're imagining that there's an acute angle. So that projection, we're projecting straight down. So we're going to find this vector right here. That is the p vector. That is the projection right down there. Right from that down. That's the projection vector. So the idea is that, let me draw another sketch off to the side here. So the idea is that we want to take vector u, and we're going to project it and find this vector p right there, and I'm going to call this one p perp. So that one's p perpendicular. That one's red. So this will be vector p. That's going to be right here, the projection of u onto v. It's a vector. We're going to call that one p perp. And so what you can see is that your vector u is going to be, we're going to be able to decompose it and write it as the sum of p and p perp.
Yeah, a couple questions. So this orthogonal projection is pretty much just finding the components of vector in relation to of using a different vector as an axis.
Yes.
And also, the orthogonal, is that in any way related to 3D graphics, where orthogonal refers to a type of camera where?
No.
Okay.
Not yet. Okay, so yeah, the perpendicular is just purely a vector that's ortho. We're only in 2 dimensions right here. We'll get to a 3-dimensional situation where we talk about a normal vector to a surface, but not yet. So here we're purely in 2-dimensional space, and this perpendicular vector is nothing more than the complement of p, so that when you add p to p perp, you're going to get back to u. So we're decomposing u into 2 vectors with respect to v. So v is kind of the new axis. That's a good way to think about it, that v is an axis. Okay, so let's try to get this notation straight. Do you agree, first off, that we can think about the result, this p vector here, isn't it a multiple of the unit vector that points in the direction of v?
Yes.
Can't we think of p as a scaled unit vector, where that unit vector is in the direction of v? Right? And that's what's going to happen here. So if we look right here, this is a unit vector. V divided by the length of v, that is the unit vector right there. So we're going to think of that as a unit vector, and then we're going to scale it. And so we need to figure out how much do we scale it by. Well, we scale it by the amount that we actually just figured out a couple slides ago. If we have a right triangle, the lower leg is cosine of that angle multiplied by the length of the diagonal, which is what this is. So just on the last slide, remember we said, oh, the component of the force, if this was a force vector in the direction of motion, it was length f cosine theta. We can just set up another triangle if you want. If that's not totally obvious to you, then you set up this triangle. Think about this triangle right here, where we're going to call the diagonal the magnitude of u, so I'll write a u with no vector symbol over it. Call this angle here, this x, we don't know. What is it? Well, if we take cosine of theta, we get x over u. So that tells us that x is equal to u cosine theta. And just remember that this u, I don't have a vector symbol over it. This one, they write it as a vector symbol, so they have to put the absolute value around it to indicate that it's a scalar, that this is the length of vector u. So that's where the norm, or the magnitude u times cosine theta comes from. So then what they do notationally is refer to this as the scalar component of u with respect to v. They want to take away the whole vector piece of it. That's the vector. This is a scalar, right? That's a number that's scaling this unit vector. And that they want to identify with its own terminology. That's the scalar component of u in the direction of v. That can be positive or negative. If you look up here, this obtuse angle generates a negative dot product, and it's going to correspond to a negative cosine value because it's an obtuse angle. So this scalar component, which they tell us right down here, can be positive, negative, or 0. Okay, so that's how the obtuse case comes in. It doesn't matter, it still works out fine because this scalar right here can be negative. So if the projection is in the opposite direction of v, if it's that way instead of that way, you have to multiply by a -1, which comes out in the wash because the angle is obtuse and the cosine of an obtuse angle is negative. So it turns out that it doesn't matter if it's acute. So you come up with the definition for the acute case, and then you take a look at the obtuse case and you realize, oh, it doesn't matter because this, if we're in the obtuse case, this cosine value is negative. So it doesn't matter. It works in both cases. Okay, a lot going on though. So let's take a look at an example. Here they kind of summarize it. Let's not look at that yet. Let's come down here and let's draw the picture, and then we'll look at this summary in a second, but let's try to get a picture of what we're doing here. And it doesn't matter. You don't need to draw this accurately, but I think it's very helpful to sort of draw this sketch every time you're doing a projection, just to sort of keep it in your mind how everything's related. And I think it's helpful to draw the vector that you're projecting onto longer than what the p vector is so that it just fits nicely and you're not dealing with blank spaces. So we're going to project, that's our p vector, there's our p perp vector. So we're going to call this one up here vector u. This one is called vector v. And then vector p is that one right there. And that one is vector p perp. So that's going to be the scenario that we're going to use repeatedly. And we need to figure out the best way to do this. All right, so p perpendicular, or p, excuse me, p, just p, the projection. So p, we're going to use that just as a shorthand notation to represent all of this. So the projection of u onto v, we're trying to figure out what that vector is, and it's called an orthogonal projection just because that's perpendicular right there. So this is going to be the length of u multiplied by the cosine of theta multiplied by v over the length of v. So again, this part right here is the scalar component of u with respect to v. All right, so that's where we're at. That formula is going to give us this projection vector. The problem right here is that, oh, dang, cosine of theta, we need the angle. We don't want to find the angle. So what we're going to do is figure out a way to get rid of that and use just the components of the vector. We don't want to have to go find the angle as a secondary piece of information. So we want to see if we can rewrite this formula in a way that only uses components and doesn't use the angle between the vectors. So what we're going to use, let's go up here now. So now we're at the point where we definitely want to look up here and use some of this stuff. So that's where we're at right now. It's like, oh, dang, don't want to use that. So what we're going to do is take this fact that u dot u is equal to the length of u squared. That's the fact that we're going to use. Let's see if we can understand that fact. So this is way easier to understand than you may think. So vector u, we're going to imagine being in three-dimensional space. So this vector has three components. The length of vector u, square root, sum of squares. The length of vector u will be the square root of the sum of the squares of the components. Tell me if you aren't sure on any step here. That's how you find the length of a vector? Now let's square both sides. The length of u squared is u1 squared plus u2 squared plus u3 squared. That is the dot product of u with itself. the dot product of a vector with another vector, you multiply the corresponding components and add. So let's look at this example right here. So if I have u equal to 2 comma 3, isn't u dot u equal to 2 times 2 plus 3 times 3? So it's equal to 2 squared plus 3 squared. Or that's 13 in this case. And if we dot a vector with itself, the effect is that you are multiplying the first component by itself, so you're squaring the first component. You're squaring the second component. So when you dot a vector with itself, you get that. You get the length of it squared. So this little formula is going to be our ticket to get rid of the angle. So let's see. All right, question on that, on how you dot a vector with itself. So if we dot in general, remember you're multiplying corresponding components. Well, we're going to do it right here with these guys, so I won't do it on the board. All right, so let's see if we can follow this then. So we have our dot product formula that we had on the previous slide, u dot v is equal to the length of u times the length of v times the cosine of theta. Now we just want to try to rewrite this. So when you look at that, we've got length of u cosine of theta right there, correct? Everyone see it? So if we want to replace cosine of theta times length of u, can't we divide both sides of this by the length of v? So this quantity right here, that quantity right there, u cosine v, or length u cosine v, excuse me, length u cosine theta, it's u dot v divided by the length of v. So we're going to replace that down here. If you look down here, that's what I just am saying. Cosine of theta times length of u is going to be u dot v over length of v. So we're going to substitute that in. So right there, replace that with u dot v over length v. There's u dot v, and instead of length v, we're going to replace it with the v dot v. Let me write it. I need a little bit more space. Let's come down. Let's come down here. So let's start. Let's do it right here. So we know that u dot v is equal to length u, length v, cosine theta. And we know that the projection vector is going to be length of u cosine of theta times v over length v. And we know one other piece of information. We know that u dot u is length of u squared. So those are our 3 pieces of information. And all we want to do is get rid of this guy right here. So we're going to come here. We're going to say that p is then equal to, so length of u cosine, that's going to be u dot v divided by the length of v multiplied by v divided by the length of v. So now we have u dot v divided by length of v squared times v. And our last step is to then use this bottom formula, the length of v squared or the length of u squared. It doesn't matter what letter I put in here. Maybe I'll put the v in there because that's the letter we're going to replace. It's a generic formula. It doesn't matter what letter you use, but we're going to use it this way. Length of v squared is v dot v times v. That is going to be our component method for finding the projection vector. U dot v, scalar. V dot v, scalar. V, vector. So this is the scalar times v. Now that's not a unit vector now because I pulled that length of v over here, so that's no longer a unit vector, but it doesn't matter. So that's going to be our way to get our projection vector. So let's try it. So that formula right there is another one you have to remember. That one we're going to use a ton. And the more you use it, the more it becomes pretty easy. So the vector that you're projecting onto, you know that that's got to be the vector that shows up over here. If you're projecting onto v, you need a multiple of times v. So the vector you're projecting onto basically shows up in every position except for that first position. So it'll be pretty easy to remember. All right, so let's do it for this one. So this is going to be u dot v over v dot v times v. So for this one here, our components of u and v, what would u dot v be?
20.
So 20 plus 30, does everyone agree with that? We're going to take the corresponding components, multiply, we get 20. Take the y components, or the second components, multiply, get 30. So that's the dot product right there. And then we have to take v and dot it with itself. So v dotted with itself will be 4 plus 36. 4 plus 36. And then we have to put vector v on the end over here. That's 2 comma 6. So this will be 50 over 40, which is 5/4, times 2 comma 6. And that distributed across is going to be 5 over 2, comma 30 over 4, 15 over 2. So that is our projection vector. There's P. All that work to get P. So that will be the projection vector. And did they ask us for both there? They didn't ask us for P perp there. We don't have a lot of space, so let's not find P perp here. All right, so look at that. And is there a question that you have on it? I'm going to put this down below. Let's move it over here. All right, is there a question on any step there?
Yes.
Yeah, go for it.
Can we go back over how we got the 20 and the 30 and the 4 and the 36?
Absolutely. So the numerator is u dot v, and the definition when we're doing a dot product is that we multiply corresponding components and add. So if we think about these as x components and y components, 10 times 2, 5 times 6, so that gives us the numerator. So we multiply the x's, multiply the y's, and add.
All right.
So there's no one little step that's hard here, but it's sort of all the steps put together. So u dot v, multiply, multiply, add. V dot v, we have to do the same thing, but we're dotting v with itself. So we're basically saying 2, 6 multiplied by 2, 6. So that's going to be 4 plus 36. Does that make sense?
Thank you.
And so the more you do it, the more you start to realize, oh yeah, v dot v is going to be that squared plus that squared. And then we take the vector v in component form, put it on the end here, and distribute that constant across, and that gives us our p vector. So let's try it up here. So here, for this one, p is going to be same idea. It's going to be u dot v divided by v dot v multiplied by v. So what will u dot v be up here?
0, 0, 30, negative 30.
Negative 30, yep. So what does that tell us right away about the angle between the vectors u and v? Obtuse. Negative dot product, obtuse angle. And then v dot v, we come to v, and we have to dot it with itself. So it's going to be 0 times 0, 4 times 4, negative 2 times negative 2. So we're going to get 16 plus 4. Let's write it like that for now. And then we multiply it by the vector v, 0, 4, negative 2. And so our last step is to combine this. So we get negative 3 halves, because we have 30 over 20. And that's going to be distributed across this vector. So we're going to get 0, negative 6, and positive 3. I need to put a plus on the 3. It's understood that it's positive. positive 3. So that's our p vector. So as you start to do it, it's not hard to do. It's the theory behind it, though, is a little bit complex. Trying to understand how you combine basically these 3 equations into one. Right. Yes?
So the end result, that 0, -6, 3, that's the actual length of
That's
P
the
as
actual
well?
vector.
It's the vector. But
So if we wanted to find its length, if we wanted to find the length of that projection vector, we would do the square root of 36 plus 9.
Okay.
That would be the length of the projection vector. So that's actually the component form of p.
Okay.
And if we want its length, we could just do square root sum of squares to get its length. There's another way, too, that we'll talk about that's kind of more clever. But we'll get to that in due time.
And just to make sure I understand, to get the unit vector, you divide by that magnitude, right?
So now we never are going to be looking for the unit vector with regard to p.
Okay.
It's always v. So we'll take v and divide it by the length of v to get the unit vector in the direction of v.
Okay.
So we won't be doing it with p.
Okay.
So let's try this one. So here's a work problem. This one's a little bit not projection vector fully, but so I want to show you one other connection with work. So we talked about this scenario where we've got a force and we have a distance that a box or something's being moved. But now watch what we can do here. So we know that work is a scalar. It's going to be the length of f times cosine of theta times d. It turns out that we can actually do what we just did a minute ago. If we rewrite the distance, the displacement of the object that's being moved, if we write it as a vector, we're going to get this. Do you agree? Right? Isn't this the same thing as the length of f? And instead of d without the vector means a distance. D with the vector means the vector d. But the length of vector d is d, so we could write it this way. All right? And that's just f dot d. Then we don't have to deal with theta again. We can get rid of theta if we turn the displacement into a vector of its own. If we can write the displacement as a vector and the force as a vector, we don't have to deal with theta. We don't have to deal with projecting the force. We don't have to find the component of force in the direction of motion anymore. We can back out of the theta and just deal with components. So here, our force vector is 432, and our distance, if we wanted to find the distance, we'd use the distance formula here, but we don't want the distance. We just want to make this a displacement vector. If we make that a vector, now it's a little funny because we're coming off the origin, so the coordinates of that endpoint are going to match the components of the vector. But, so it's a little funny. If this was vector, let's just look at a hypothetical here. If this was vector 0.120, so if we went this way instead, just to be clear, then our displacement vector here would be 7, 4, 0. 7, 4, 0. So just to sort of make it clear that, it looks a little funny, 860. It's not always going to match the coordinates of that point. It's only matching the coordinates of that point because the initial point is 0, 0, 0. So we're finding the displacement vector from 0, 0, 0 out to 860, which of course coincides with the vector in standard position. But now we can find the work so easy. So we get 32 plus 18, what's that, 50? And work is usually in Newton meters, force times distance, Newton meters. So that's kind of nice that we can actually find the the work, without having to calculate the angle between the force and the direction of motion. So all we did was turn d into a vector, and lo and behold, now that we know what the dot product is length times cosine. Then it all falls out.
Guess you could say it's work with a little less work.
It's a little less work to get the work. You got to work smarter, not harder.
I'm slightly confused as to how you just decided to make the magnitude
Mhm.
of the distance a vector. Like you just assume it's a vector, just like turn the points you're given into a
So
vector.
so we're going to use this convention throughout the semester that if we write v, that means that it's the length of v.
Yep.
So if you're dragging a box from here to here, and you know the distance is 10, you can imagine the coordinate system there, and then
Okay,
make
yeah.
that the vector 10, 0.
Got it. Okay.
So you can turn you can just turn that displacement into a vector,
Yep,
got
got
pretty
it.
readily. And it's amazing that it all works. That's still, so the moral of the story, work is still force times distance. Right? Still force times distance. It's just that instead of the simplest case where it's force with no vector and distance with no vector, now it's force times distance with vectors on top. Yeah, but it's still the same simple formula, force times distance. All right, so here we go, another decomposition for the following vectors u and v. Now here, they write the normal vector instead of p perp. I will write it, I think it's a little, I really like to leave this second vector as p perpendicular. I feel like it's a little bit easier to visualize that those vectors are really connected. P and p perp are coming together as a right angle. So let's figure out p. So p, that's the projection. And I always will write it just as p. I'll write this stuff up here just to emphasize, but that's kind of a cumbersome thing to write every single time, projection of u onto v. Of course, if you feel more comfortable writing that, if that helps you, do it. But if you want to use shorthand notation, just write p. We know what p means in this class. It means the projection of u onto v. And so the formula, we've got a u, and then it's all v's after that. It's going to be u dot v divided by v dot v times v. So that's going to be the formula we use most frequently for the projection vector. That other formula, the length of u times cosine of theta, we're not really going to use that. That was just sort of a theoretical way to get to this, because this is super practical. You know the components of u, you know the components of v, you can figure out the projection vector with no theta. All right, so u dot v, what is that equal to? 7? Everybody okay with that? So 4 times 1, 3 times 1, add them together. So we have 4 times 1 plus 3 times 1, add them together. V dot v?
2.
1 plus 1. So we square that, we get 1 plus 1, and then v is v. So this gives us 7/2 as the multiplier, as the scalar. We're going to jump it into the vector, so we'll get 7/2, comma 7/2. That is our projection vector. That is p. That is the projection of u onto v. That's a vector. And they also asked us to find p perp. Well, let's do a little algebra over here. We see that, oh, p perp, that's just the original vector u minus the projection vector. P perp is u minus p. So p perp we will find by taking u, 4, 3, subtracting off the projection vector, 7/2, 7/2, and that is going to give us 4 minus 3.5 is 1/2. Looks like 1/2 and minus 1/2. So that's our p perp. So p plus p perp is going to give us u. P plus p perp gives u. So in practice, the problems aren't that complicated. It's just sort of getting all that notation. Cal 3 is a ton of just notational soup that you just got to sort of play with and move stuff around. Any questions on finding p or p perp? P or p perp?
Maybe I'm just looking too much into it, but isn't it pointless to find p perp if you have to use? Isn't it pointless to define u as p plus p perp if you have to use p perp to get, or rather you have to use p to get p perp?
Can you say that again faster?
No.
I mean, the idea is so you've got your u, you've got your v, you find the p, and notice with vectors, so here's p perp, if your goal is just to find the length of p perp, there's going to be a way that we can bypass not finding p. There's going to be a way. But the idea is going to be that this vector p perp, you can move it wherever you want. And do you agree that you could move it right there? So you can move it right inside the two vectors that you started with, u and v. And what we're going to see is that thinking of p perp as being right there is going to give us a shortcut to a couple of applications in a little bit. But if you only are interested in the length of p perp, there is a shortcut. You don't have to find p, and then there'll be a shorter way to do it. But we'll get to that. All right, let's take a look at this cool application. So, distance between a point and a line. And this works whether you're in two-dimensional space or three-dimensional space. Gives you a really slick, general way to find the distance between a point and a line, which is a very practical thing to have to do if you're a scientist. So find, okay, here's what we're going to do. So let me explain the concept of it first, and then we'll look at the mechanics of it. So the idea here is that we've got this line, and we have the point P not on the line. So just a line and a point, and we want to find that distance. So i.e. the shortest distance, that perpendicular distance. That is, by definition, the distance between two geometric objects. It's the shortest of all possible distances. Right? You could say, oh, well, isn't the distance from here to here? Yeah, that's a distance, but that's not the shortest distance. We define the distance between P and the line to be that shortest distance. So here's what we're going to do. We're going to find a random point, any point, on line, what do we call the line? L. Perfect, line L. So any point on line L, that's going to be Q. We'll probably try to use the same exact lettering throughout all these applications too. So we can then form this displacement vector from Q to P, call it U. All right. So line, point P off of the line, point Q is on the line, form that displacement vector. What we see is that D is that distance right there, but isn't that the length of P perp? Mm-hmm. That's going to be the length of P perp. So we look at U, we have our line, we're just taking away the line and focusing on the V, the vector V for a minute. So the projection, and they called it W, I would prefer to call it P perp, of course, but they called it W in this application, so I left it as W. Let's put P perp out here just as a reminder. So the distance that we're looking for is right there. So the distance that we're looking for is the length of P perp. It's the length of this vector W over here. So we find vector W, and D is going to be the length of that vector. Okay, that's what we're going to do. That's how we're going to find this distance. Yeah?
Why not just put a vector where D is?
First
place. Why bother with
okay.
Q?
There you go.
Yeah, but why bother with vector U at all?
Well, vector U or W?
He's saying essentially move the Q point right underneath where P is.
Oh, move Q to there?
Yeah.
You can't find that point.
What?
That point's unknown.
You said pick any point.
Oh.
Any point. The chances of you picking the point that happens to be right below?
So you do know the location Q, you do not know the location of what's directly.
Yes, exactly.
Okay.
Now, if we had a way, if we had a magic 8-ball and said, pick the right point, I want to see you pick the right point. That would be beautiful. If you pick the point that happens to be right below, you should be buying lottery tickets and sharing. Yeah. So yeah, there is a chance that this point Q you pick is right below, and it will all come out in the wash, but 99.9% of the time you pick a random point on that line, you're not going to be anywhere, I mean, maybe you're close, but you're not going to be right at it.
Okay.
Yeah. That would be, yeah, you would have how could be your superpower? I can identify the point closest to an object. All right, so let's go ahead and work through this one then. So this is what they're doing. All this talk up here is what they're explaining this. So we're going to start here. So P is the point 2, 5. excuse me, 2 comma negative 5. 2 comma negative 5. Q. All right, they tell us that this line is y equals 3x. That's the line, y equals 3x. Somebody give me a point on that line.
3, 1.
Okay, good. A point on a line has to have two coordinates. So what was the point?
3, 1.
3 comma 1's not on that line.
3, 9?
3 comma 9 is on that line.
1,
And 0 comma 0 is on that line, so there's a whole bunch of points. Let's not pick 0, 0 just because that sometimes makes things look differently than in general. So let's pick something like, let's pick 3, 9. 3, 9's fine. So 3 comma 9, that's a point on the line. So now what we're going to do is form this vector u that is off of the line. So that, we have a vector from q to p, so if we want the components of this vector here, we're going to do tip minus tail, p minus q. P minus q is -1. That minus that, -14. So there's vector u. Vector u. Now we're ready to find vector v. So vector v is a vector that is pointing in the direction of this line. This one's a little bit more tricky to think about. How do we figure out the direction of that line? How do we find a vector that's pointing in the direction of that line?
Could you just pick a second point on the line?
Perfect. Perfect. So on the line, we can say we've got 3 comma 9 is on the line. We can also say 0 comma 0 is on the line. So if we want to form a vector that is pointing in the direction of the line, boom, right there. 3 minus 0, 9 minus 0. That points in the direction of the line. Could you also pick 1 comma 3? Would that work? Yeah. That would also work. It doesn't matter if you scale this vector, if you make it bigger, longer, or if you make it shorter, it's not going to change the direction. So we can scale it down to 1 comma 3, get rid of some common factors, maybe have smaller numbers. Right? We just need any vector that points in the direction of the line. Right? If 10 comma 100 pointed in the direction of the line, so would 1 comma 10. You can scale it back and you have not changed the direction the vector is pointing. If you divide by a common factor all the components, your vector is still pointing in the same direction. So why not? Let's divide by 3 to make that just a vector with slightly smaller numbers. Cannot hurt. So that gives us a vector v. So now the projection vector p is going to be u dot v divided by v dot v times v. So u dot v, -1, -52. Is that right? 30 plus 12. No, that's not right. 42, right? Started thinking about cars. That's not right. There's not 3 14s. That's 42, correct? 30 plus 12. And then v dot v is going to be 1 plus 9. And then vector v, we just leave it as it is, component form. I'm just going to move these guys out of the way. Put them over here. All right. So vector p, the vector p is going to be minus 43 divided by 10 multiplied by 1 comma 3. So that's going to be negative 43 tenths, comma, negative 129 tenths. I think. Yep. So that is our vector p. Vector p perp, or in this case they called it w, that's going to be vector u minus vector p. Vector u is the vector we started with, -1, -14. Minus p. I'm going to distribute the minus sign to make it a plus. So we're going to add those together. So we'll get 43 over 10 minus 10 over 10, which is 33 over 10. And then we're going to get 129 over 10 minus 140 over 10. So that's minus 11 over 10. Then the culminating event, the magnitude of p perp. That's going to be the square root of the sum of the squares. And that will be the length that we're looking for. I don't know why I'm going all the way back up there. So then we square, square, add. When we have a calculator, it's starting to get a little messy. So 33 squared over 10 squared plus 11 squared over 10 squared. So we're going to get something over 10. Oh, we could factor out an 11. That would be kind of clever. Factor out 11 squared. If we factor out 11 squared, it's going to come out as an 11 and leave a 2. Is it 22 over 10? It can't be that simple, is it?
Do it, but there's some pretty fast kids in here, so I figured they'd have it
Yeah,
by now.
yeah. It feels like it might actually come out really nicely. 33 squared,
121 over
11 squared. Yep, so that's 121 times 10. So and we're square rooting it. Square root of 121 is 11. So isn't that 11 root 10? Does that look right? So that will be the distance then between the point and the line. So now if you wanted to find that point that was in fact the closest point, you can actually find it now that you know this distance. It takes a little bit of work, but you could do it.
I get 11.
Yeah.
Just 11. From
Oh,
from alpha.
Yeah, I get 11 over.
Well, 11 over the square root of 10 is that.
Okay.
That's the same thing.
No, because you factor out the 11 square out, so you get 3 square plus 1 square.
Well, if you pull 11 squared out, you get 3 plus 1. Not 3 squared plus 1 squared.
Yeah, that's right.
If you pull out 11 squared, it comes out as an 11. The 10 squared comes out as a 10, and you're left with 3 plus 1, which is 2. Oh, yeah, it shouldn't be square root of 10 then.
Oh, you got it. It was 11 over root 10, but you just rationalized it.
Yeah, yeah, I think that's right. 11 squared, 3, 11 squared, 4 squared. Do we agree that that's right?
Yeah.
Okay, all right, good. All right, good. Let's go to the next slide. Let's do more.
Just to clarify, that 0.39 was totally just arbitrary. We just
Yep.
pulled that out of the air.
Yeah, should we do it with a different point and see what happens?
No. No, I just want to make sure.
Whoa! No.
That's right.
No. All right, so here's the next one. So here is going to be your point. You guys are going to do this one now. So the point not on the line is going to be 1, 2, -1. And the line, we're going to talk about the line as, let's see. Let's say the line is y equals, let's not get too complicated. Let's make it like 2x plus 1. And oh, but we're in 3-dimensional space. So let me move this down to just 2 coordinates. It does work in 3-dimensional space, but we haven't talked about the equation of a line in 3-dimensional space yet. Does anybody know? Is there an equation for a line in 3 space?
There is if you have one of the components is 0.
Wouldn't
Can
it
it
be
just be like x equals 1, even if it's in 3 spaces and
So
it's just the same?
x equals 1 is a point if you're in R1. It's a line if you're in R2, but it's a plane if you're in R3. Is there a Cartesian equation for a line in 3 space?
I'm guessing it isn't ax plus by plus cz equals d. Is that?
That's a good selection, so let's take a look at that. So you just said that. Isn't that the simplest equation with 3 variables? The simplest type of equation in any space is the linear equation. So here, in 2 space, the simplest equation is ax plus by equals c, linear equation. So in 2 space, ax plus by equals c is certainly a line. But if we extend that one step, that would be, if there is a Cartesian equation for a line in a 3-dimensional space, that's what it would be. But you already know what that is. What is that? For example, what is that? It's a plane. Who said sphere? There's no squares in there. To get a sphere, you have to bend. You have to have squares. No, not a sphere. Not a sphere. It's a plane. It's a plane.
Could you technically just express a line in 3-dimensional coordinates as a vector of infinite length that
Yes.
just points in a direction?
The only way we're going to be able to express a line in 3-dimensional space is with a direction vector and then a variable that scales it. So this right here is a plane. So the simplest equation in 3 variables is a plane. So this tells us there's no Cartesian equation for a line in 3-dimensional space. If we want to describe a line, we have to do it in a different way. And so that's what we're going to use vectors for. But you've dealt with 3-dimensional space enough, and it seems really counterintuitive that there's no Cartesian equation for a line in 3 space. Right? It feels like there should be, but there isn't. So yeah, the simplest equation in 3 variables is a plane. Plane, yeah.
Yeah, weird question that gets a bit off topic, but
Okay, let's hold it then.
Okay.
Let me finish explaining this first. So you have a point that's not on the line. This is your line, and the question is, let's just first make sure that I didn't somehow get lucky and pick a point that was on that line. Okay, this point is definitely not on the line, right? You plug in the 1, the y value associated 1 would be 3, so it's definitely not on the line. All right, so we have a point distinct from the line, so find the distance between the two. So again, draw a sketch. A sketch for these problems is really, really helpful. So this would be the picture that you should be drawing that is going to help guide you to get to the right answer. So I'll just draw it one more time, but you guys should get to the point where you can draw these. All right, so there's your picture. So see if you can calculate this distance.
Oh, what about the secondary point? The one at the center of P and P perp. Are we going to pick that one arbitrarily, or do you want to pick that one yourself so then everyone has the same similar answer?
We're all going to get the same answer. There better only be one distance.
Oh, yeah, okay.
Right? There better only be one distance, and it's not going to matter what point you pick or what vector you pick. As long as your point is on the line, and as long as your vector is truly pointing in the direction of the line, it won't matter. It will not matter. If you're getting snagged, raise your hand, and I'll point you in the right direction. Down the right direction. Is that supposed to be on the line? So if you plug in 2, you get 5. So this point is certainly on the line, and so you want a second point on the line so you can form that vector. So if we pick this point, and then second this, 1, 2, 1, 2. This is a point, not a vector, so that's just parentheses. So then another easy point to pick is 0, 1. So let's make that point 0. Let's not call it P though, let's call it anything that's U0. And so now you can form the displacement vector between these two things. Those are both on the line. So then if you do 2 minus 0 and 5 minus 1, that'll be the vector that points in the direction.
Displacement vector is U, and then V is
No, V is the displacement vector. U is going to be the vector between the point and one point on the line. So if you choose that as your point on the line, your first point, then you're going to do 1 minus 0, 2 minus 1 for u. V is going to be this minus this.
Okay. Okay. I thought I was getting confused.
Yeah, there's a lot going on for sure. Anyone else? Where are your points on the line?
You know what, actually, I'm kind of lost on this.
So you've got one of them, that's on the line. Plug in 1, you get 3. So if we want to find that vector that points in the direction of the line, we need a second point on the line. So what's another point on the line?
I mean,
2, 5? 5? Yeah, absolutely. And so now you have 2 points on the line. You can now form a vector on the line. So if you subtract these 2 points, that's going to give you a vector that's pointing in the direction of the line. So that's first step. Like that'll give you a V.
I'm confused too.
Yep. So that's a vector V that points in the direction of the line. So now we need our vector U. So you use this point already. So let's now find the vector between these 2 points.
The line
I'm actually kind of not understanding the concept of like this is a line that I'm used to this, and I'm just when I do this, you know.
Yeah, if you want to graph the line.
Yeah, like I want to do that, but then you're saying that this is
Yes.
that.
Yeah, we're looking at this as a reference picture. We're not looking at this as an actual picture. We want to, a lot of times in Calculus 3, you're going to be projecting, and in order to remember your formulas, you want to have one image that works with every type of problem. So if you start drawing things in different positions, it will work, but it's a little more complicated in terms of memorizing formulas. So this line, you're absolutely right. That line is this line. Yes, that line is
Then this line
is going to be from the point that you pick out to.
You want us to do the whole thing? Should we do everything we did on the last one?
Going up
We'll hopefully answer all questions. Okay, so one question that just came up, this line 2x plus 1, you can draw that accurately in the Cartesian plane, but you don't need to. That's not going to add any value to figuring out the answer to the problem. What you typically want to do in Calc 3 when we're dealing with a lot of this geometry stuff is coming up with a sketch that you use again and again and again and again, regardless of what the line looks like or what the surface looks like. Because we want to be able to do this in 3-dimensional space also once we get the equation of a line in 3 space. And we can't draw that. You're not going to be able to draw that and get any value out of it. But here you can use this general sketch, 2 space, 3 space, or more space. You can use, I'm like Dr. Seuss there for a minute. More space.
Red
So
space, blue space, 1 space, 2 space.
green space. So what we're going to do is find any 2 points on this line. And now I'm going to draw them here just at the left of the vector and the right of the vector because that's kind of what vector v would represent then. So I'm going to pick 2 points on the line. I'm going to pick 0, 1, that's on L. And I'm going to pick 1, 3, that's on L. So both of those are on L. Those 2 points are on L, so I can form the vector v. I'm going to subtract this way. Again, it doesn't matter which way you subtract either. It doesn't matter if the vector is pointing this way or that way. I'm going to subtract in a way that I don't get negatives. So that vector v is this vector right here. It's connecting 2 points that are on the line. Now I have a point that's not on the line right there, 1, 2. So now I want to form the vector u. The vector u, I'm going to go from this first point, which I'm calling 0, 1, out to that point. So I've got to do the point minus 0, 1. So it's going to be 1 minus 0 and 2 minus 1. So that's going to give me a vector 1, 1 right here. So we now have 2 vectors. Both those vectors are pivoting off 0, 1. We pivoted in the direction of the line, and we pivoted in the direction of that point that's off the line. So now we can find our p. P is going to be u dot v divided by v dot v times v. So u dot v is 1 plus 2. V dot v is 1 plus 4. V is 1, 2. So this gives us 3/5 comma 6/5. If we multiply that out and distribute it. So 3/5 times 1, 3/5 times 2. That vector is the p vector right there. To get the p perp vector, we're going to take the original vector that we found for u, which was 1, 1. We're going to subtract off 3/5 and 6/5. And that's going to give us 2/5 and -1/5.
Yes.
Then we're going to find the length of that, and this is our distance. This is the number that you are looking for. 4/25 plus 1/25. That's 5/25. So that's the square root of 5/5. So that right there is our distance. All right, let me pause. And so question, we only have a few seconds left, so is there a question? And I can stay and answer any slow questions if we want to go through it very slowly. Any questions? Yeah.
So with the vector u,
Yep.
you make that by choosing a point on that same line L?
Yep. So we've got our line L. We're going to pick one point and displace to P to get U, and then a second point on L to displace to get V. And once we have those two vectors, we're projecting U onto V, and then we do our U dot V over V dot V times V.
For me, you're so kind.
For you.
All right.
All right. Have a great weekend. I'll be checking email. If you have a question, you can email me. I have office hours for the next hour if you want to go over any math questions. You're more than welcome. We can probably just stay in here and do some math. Yes. Further? Is that good? Yeah.
It's still not working. So this is in Chrome.
All right. Let me save these notes real quick, and then before I forget, I don't want to